Share Conference presents Aubrey de Grey, Sens Foundation.
There we go, marvellous. So this is my first time in Serbia. I'd like to thank you all for turning up. I'd like to thank all these people at the front for feeding me the most lethal Serbian alcohol last night, which has actually meant I've had a rather slow start to my day. This is what I'm going to be talking about. Not exactly how to live forever, as was suggested by the previous speaker, but I'll come back to that. I think I'm working on the world's hardest problem, and the world's most important problem in particular, so perhaps I am saving the world. This is why I say that. A lot of people get this wrong. A lot of people think that dying of aging means dying of sort of natural causes, dying without having had the diseases that we know we don't want to get, Alzheimer's disease and cardiovascular disease and diabetes and so on. But that's not true, because those diseases, of course, they are all diseases of old age. They don't affect young people nearly so much anyway as they affect old people. And there's only one way that a disease can be a disease of old age, namely, if it is some aspect of the later stages of aging, some aspect of the later stages of a process that goes on throughout life and which is harmless for a long time, but eventually not so harmless. So we have to include all those diseases when we ask who dies of aging. And if we do that, then we get numbers like this. This is the number of people who die of all causes worldwide each day, around 150,000. 2/3 of those people die of aging. And of course, in the industrialized world, where not many people die of malaria and so on, it's a much higher proportion. It's something like 90%. So that, to me, is a complete, unequivocal proof that aging is humanity's worst problem. And that's why I work on it. And I mean, also, let's face it, what part of this is it hard to understand? Even if you do die of natural causes, it's still not much fun. Most people would prefer to be this guy here, even if he is about to have his head bitten off by a shark. So there's a foundation, a charity, that has been created around my work, and we are based in California, but we also have operations over here in Europe, and we work on trying to do something about aging. Specifically, as I will explain, we are interested in applying regenerative medicine to the problems of aging. So I'm going to start by telling you what regenerative medicine actually is, and then I'm going to talk about what aging is before I can really describe how we might use regenerative medicine against aging. Regenerative medicine is a way of restoring the function of the body by restoring its structure. In other words, if the body has acquired some kind of damage, whether it's the gradual, chronic, lifelong damage of aging, or whether it's acute damage from injury, like spinal cord trauma or something, regenerative medicine is about repairing that structure, putting it back to something like how it was before the damage happened, and thereby restoring its function. So you have heard already of some types of regenerative medicine. I guess everyone here has heard of stem cells. Stem cell therapy involves putting cells back into the body, which the body is not automatically creating by the division of other cells. Tissue engineering is another well-known part of regenerative medicine. It involves putting an entire organ back into the body, a replacement organ that has been created in the laboratory, outside the body. So regenerative medicine has many features to it, but there is also molecular regenerative medicine, which means repairing the insides of cells, or, for that matter, repairing the material outside the cell that holds our organs together. And all of those things turn out to be important when we want to apply regenerative medicine to aging. So now, what is aging? There are lots and lots of definitions of aging, and most of them are not very useful for trying to think about how we might develop medicine against aging. This is a really good definition for that purpose. First of all, this definition says aging is a side effect of being alive in the first place. So metabolism is the word that biologists use when they want to talk about all of the processes that go on in our bodies all the time that just keep us going. And pathology is the word I'm going to use to describe all of the things that go wrong in old age. So metabolism eventually causes pathology. That's part of this definition. But the other part of this definition is to describe, in a very brief way, how metabolism causes pathology. The way it does it is by creating damage. And I'm going to use this word damage in this very precise way. Damage is the set of intermediates between metabolism and pathology, the set of molecular and cellular changes that metabolism creates as side effects of its normal operation, but those changes accumulate. And our bodies are set up to tolerate a certain amount of those changes, but not an infinite amount. So eventually there is too much damage and we start to get the pathologies of old age. Here's the first reason why that definition is so useful. So here's my definition at the bottom. The first thing we can say is we can distinguish two traditional ways of thinking about medicine for aging. I'm going to call those ways the gerontology approach and the geriatrics approach. So the geriatrics approach is basically what we have today for the diseases of old age. It involves essentially treating those diseases just like any other disease, trying to essentially cure it, get rid of the symptoms and the causes of the pathology. And it doesn't work very well, as you've probably noticed. People still get sick when they get old. The reason they get sick, ultimately, is because this is intervening too late in the game. The things that are targeted by geriatricians are caused by this accumulating damage, and it carries on accumulating. So the geriatrician's job gets harder and harder as the person gets older. So the geriatrics approach just can never work. It's better than nothing, but only a little bit better, and that's how it always will be. So many people have realized this a long time ago, and that's why people have been talking about the gerontology approach, which says maybe prevention is better than cure. Maybe we can have more of an effect if we try to clean up metabolism and slow down the rate at which it creates damage in the first place. That sounds much more promising. It would certainly have the right effect. It would delay the age at which pathology emerges. But there's a problem with the gerontology approach too. Here's the problem. Metabolism is rather complicated. This is, as biologists among you will know, this is a simplified diagram of a small subset of what we know about how the body works, about how metabolism works. And as you can see, it's pretty complicated, and it's pretty challenging to think how we could possibly tweak this process, this network, in a way that slowed down the creation of damage without in some other way having effects that did more harm than good. We just can't do it. We don't know enough. And that's the key thing. You know, I said this is a simplified diagram of a small subset of what we know, but the real problem is that it's a simplified diagram of a small subset of what we know about how the body works, which is completely dwarfed by the astronomical amount that we don't know about how the body works, even ignoring all the stuff that we don't even know that we don't know. So it's completely, the gerontology approach is not completely doomed in principle the way the geriatrics approach is, but it's an idea whose time has not nearly come. So this is all rather depressing, isn't it? Neither of the approaches seems to be promising, but I wouldn't be here if that were the end of my story. So what's the solution? Well, the solution is a third approach, and I'm going to call it the maintenance approach. And this is the application of regenerative medicine to the problem of aging. The maintenance approach says let's not try and slow down this process where metabolism creates damage, and let's also not try and slow down the process where damage creates pathology. Instead, let's try to separate those two processes from each other by periodically going in and eliminating this damage, cleaning it up, repairing it, so that even though metabolism is creating damage, it doesn't reach the level of abundance that is bad for us. And this, first of all, of course, avoids the problem of the downward spiral of the geriatrics approach, because the target of the maintenance approach does not have any accumulating precursors. By definition, it's the lifelong accumulating damage that is created as the immediate side effects of metabolism. But also, this approach is very promising compared to the gerontology approach, because here we're not proposing to interfere in metabolism itself, only to wait until metabolism creates some damage and then repair it. So we're not proposing to actually slow down the rate at which metabolism creates damage in the first place. So that's why I think it's pretty promising. But it gets better, because we can actually describe in very clear details what damage actually is, what the targets of this regenerative maintenance approach should be. This is all the damage. 7 major categories of molecular and cellular alteration in the composition of the body that are caused as intrinsic, normal side effects of the way the body works, and which accumulate throughout life and eventually contribute to ill health in old age. So I don't have time to go through this list in detail, but you can see the sorts of things we're talking about. Cell loss, that's just cells dying and not being automatically replaced by the division of other cells. And as I mentioned earlier, the way to fix that is essentially stem cell therapy. The other things here are equally specific. So you can have too many cells because cells are dividing when they're not supposed to. That's what cancer is, of course. You can actually have too many cells in a different way by cells not dying when they are supposed to. It turns out that that's important for the aging of the immune system, for example. You've probably heard of mitochondria. Mitochondria are the part of the cell that does the chemistry of breathing, extracting energy from nutrients by combining those nutrients with oxygen. And mitochondria have their own DNA, which accumulates mutations, which are bad for us. We get molecular garbage accumulating inside cells. Just material that's created as byproducts of normal metabolism, but the cell doesn't know how to break it down or to excrete it, so it just piles up. And eventually it gets in the way. That turns out to be the reason why we get cardiovascular disease, because certain derivatives of cholesterol accumulate in cells in the walls of our arteries, and eventually those accumulations make the cells not work, and the cells start to get inflamed, and other cells come in, and they get the same problem, and you get an atherosclerotic plaque, which is what causes heart attacks and strokes eventually. The main cause of blindness in the elderly, macular degeneration, is also caused by the same sort of process, a different type of junk, but still the same problem. You can get molecular garbage in the spaces between cells as well, extracellular junk. That happens in Alzheimer's disease, the accumulation of something called amyloid. You can also have stiffening, loss of elasticity of the lattice of proteins which holds our cells together, holds our organs together. That's called the extracellular matrix. That stiffening happens because of chemical reactions with circulating sugar molecules, and we need to fix that too. Why do I think that this is really all we need to fix? Well, here's one reason. We haven't added to this list for 30 years, since way before I was working in this field. It's been 30 years since anyone came up with anything that doesn't fit into this characterization, this classification, that contributes to age-related ill health in humans or in mammals. Another reason is you can just look at what we're made of. You can say, well, what are the long-lived structures in the body that could accumulate damage? And you can get more or less this list that way too. So that's pretty good news. But here is the really good news. This, on the left, is the same list that I showed you a moment ago. On the right is the ways that we can go about fixing these things. I already mentioned cell therapy as the way to fix cell loss, but all of these 7 classes of damage can be addressed, not necessarily by therapies that exist today, but by therapies whose design exists. In other words, therapies which we can see how to develop, starting from what we can already do and what we already know. So, of course, I don't have time in the 5 minutes I have left to go through all of these, but I do want to give you an idea of how much progress we are making and how close we are to getting somewhere. First of all, we have actual clinical trials of many of these things. Stem cell therapies are in clinical trials for a number of different indications, including some aspects of aging. For example, Parkinson's disease is caused by cell loss in a particular part of the brain, and some clinical trials for Parkinson's disease are using stem cells, and sometimes they are very, very effective. This is actually still at an early stage. Sometimes it doesn't work, but when it does work, it works spectacularly. So that's just one example. I've also mentioned down here the extracellular junk. In Alzheimer's disease, the amyloid that accumulates can be eliminated using vaccination. And that is also in clinical trials. Actually, that's in phase 3 clinical trials. It probably won't be a complete cure for Alzheimer's, but I think that it is likely to be part of an eventual cure. If we go on and look at some of the other parts of this list, they are at an earlier stage. They're not in clinical trials, but they're still making headlines. This one here is an interesting one. These cells that accumulate inappropriately because they're not dying when they're supposed to. Turns out that there's a way to show, first of all, that those cells are important in aging, and secondly, that when you get rid of them, you have a big therapeutic effect. This paper came out about 6 months ago. It was, of course, not in humans. It was only in mice, but still, mice are pretty similar to humans, really. And they genetically engineered these mice so that they would accumulate these death-resistant cells more quickly than mice normally do, and sure enough, the mice died at an earlier age than normal, and they look pretty unhappy. But they also engineered these mice so that by giving them a very simple drug, they could eliminate these cells that were accumulating inappropriately. And when they did so, this is what the mouse looked like after a little while of recovery. And in many, many ways, the mice were healthier. This is one of just more than a dozen different things that the researchers looked at to see how much was better. This is to do with the thickness of muscle fibers, which is something that goes down during aging. And that was just one example of how well this therapy worked. In Sens Foundation, we work on the hardest of the 7 types of damage, the ones that are at the earliest stage and are not being much worked on by other people. This is the beginning of atherosclerosis, the beginning of cardiovascular disease, the accumulation of modified cholesterol in the artery wall in cells that are supposed to be dealing with cholesterol. They get poisoned. In particular, this part of the cell, the lysosome, gets poisoned, and they turn into this thing, a foam cell, which can't handle normal cholesterol or any kind of fat. That's where atherosclerosis comes from. What we're doing is environmental decontamination. We are using enzymes from bacteria that break down this stuff, and we're putting them into our own cells. This is a simplified description of why cholesterol does not accumulate in graveyards. Young people turn into old people and eventually into dead people through a variety of processes, of course, but one of them is the accumulation of cholesterol in the arteries. But then dead people turn into decomposed people. And they don't do it because of something that's in our genes. They do it because of things that are in the genes of microbes in the soil. And so what we have done is we have looked into those microbes. We've found them, and we've asked, how are they doing it? And we have found enzymes that break these things down, and we have started to introduce those enzymes into our own cells so as to counteract the process that turned young people into old people in the first place. And it works pretty well. This is just preliminary data, but it's very encouraging, showing that if you have too much of this stuff, then the enzymes don't work. They are overwhelmed. But if you have a modest amount of this toxic material called 7-ketocholesterol, which causes atherosclerosis, then having these enzymes and targeting them to the right part of the cell where the toxic material is, the lysosome, causes improved survival of the cells. This is what's being measured by this fluorescence. that's improved relative to all of these negative controls where the cells don't have the enzyme or the enzyme is targeted to the wrong part of the cell or something. So, I only have 30 seconds left, but if you want to know more, you can either come to the Q&A that I'm doing at 3:30 in the other room, or, of course, you can also get hold of this book, which I wrote a few years ago, Ending Aging, talks about all of these things in great detail. There's an entire chapter in this book for each of the 7 different types of damage and the ways that we're going about fixing it. So I hope you will be able to get hold of that. And, of course, you're always welcome to visit our website or to email me. There's my email address. So thank you very much. I hope to see some of you at 3:30.